Okay, let's now look at some implications of the Heisenberg uncertainty principle. In particular, we want to sort of see how the uncertainty principle might be relevant in some experimental situations. Okay, and we're not really concerned here with the uncertainties that are associated with a limited precision of our measuring instrument. So we can imagine that there's certainly any instrument has an inherent precision limit um, that will give rise to some uncertainties, but that's not what we're after here. We're basically going to assume that whatever instruments we're using to make um, some measurements are perfect in the sense that they have no systematic uncertainties. Okay, no limits on their precision, and we're looking for some fundamental limitations that arise from the uncertainty principle. And so we can let's just look at a couple examples. So as a first example, let's think about using a lens to focus light, maybe laser beam, and I've basically depicted that over here. So basically what I've drawn is a lens with a diameter d, okay, and a focal length L, okay, and it is taking a beam of light, which is sort of indicated by this these dotted lines that are coming in as if the beam of light is coming from the top, okay, and they're focusing the light to a focal point, okay, and the focal point at A. So A just marks the spot that the light comes to a focus, and we'll just define this direction here, this horizontal direction that's in the plane of A, that in which the A is a point along the x-axis here. And we want to sort of see what sort of fundamental limitations arise from Heisenberg uncertainty principle in this kind of situation. And the first thing to realize is that I've drawn this as, again, kind of a beam of light, but what we know is that a beam of light is actually composed of individual photons, individual particles called photons, and each one of these photons, can denote a photon by the letter gamma, and just draw a circle to kind of represent its position in a particular time, has a trajectory, and obviously the job of the lens is to sort of bend the trajectories of any photons that are coming in. Okay, here's maybe another photon towards the focus. Okay, so that's what the lens does. All right, and and so let's think about this now in terms of the uncertainty principle. Well, one of the first things to realize is that any photon which arrives here at A, okay, this position, obviously must have come through the lens if we block the light coming from all other places. But any photon which arises here, we cannot tell from which position it came from on the lens, just like we couldn't tell in the double slit experiment which slit the light went through, which slit the photon went through, or any other particle. That's why you get interference, is because you can't tell which slit it goes through, basically. And so we can't say which we cannot designate a position from which the photon came on the lens when it hits when it arrives at point A. Okay, we can't do that. And so so let me just draw another photon here going this direction, and the lens bends its trajectory towards the photon, towards the point A, the focus. And let me just indicate this angle here from the vertical as theta, and then the maximum angle would be a photon that goes right along the edge of the lens. It obviously is going to come at the biggest angle here, theta max.